Welcome to the Merlin and Metro News Network. Today's program will cover the cargo door and latching system. And we'll cover one of the Merlin and Metro mechanics' favorite subjects, click-clacks. So sit back and let's roll our first program.
The Merlin and Metro cargo door is used to close the cargo door opening and, when latched, becomes part of the aircraft structure for carrying flight and pressurization loads. The door itself is constructed in conventional fashion. An outer series of frames is supported by internal ribs and braces. In addition to providing structural strength for the door, these items also serve as mounting points for the door latching mechanisms. A one-piece outer skin is riveted to the door structure. The skin is trimmed to extend past the door framework to create a rest for an inflatable rubber door seal. Latching the door into the aircraft structure is accomplished through special expanding latches, more commonly referred to as click-clacks. Each latch consists of a center shaft, an internal spring and spacer assembly, and 4 jaws which surround the shaft. As the shaft is pushed outward, a ramp on the shaft will extend the jaws, as well as force them to expand. It is the expansion of these jaws that makes the latching system unique. The bayonet latching system, used on the passenger door, restrains the door against shear loads only. Because of the expanding nature of the click-clacks used on the cargo door, these devices can also carry tension loads. This ability to carry loads in 2 directions allows the closed cargo door to become a load-carrying part of the aircraft structure. We'll use this cutaway click-clack to explain its operation in more detail. Here is the basic shaft assembly. It consists of the shaft itself, a backup washer, a spring, a locking washer, and a bushing that carries the jaws. The spring side of this bushing is cut at an angle. The jaws are assembled into the unit as shown. Notice that the fully retracted jaws fit behind the tip of the shaft. Even with the jaws in this position, there is still the possibility that the jaws could hit or hang up on the receptacle in the door opening. If this were allowed to happen, it is possible that the center shaft could continue on into the receptacle without the jaws. The tip of the center shaft would actuate the warning switch and the door would appear latched. But the jaws, which actually carry the load, would not properly be in place. To prevent this, the jaws are prevented from moving until they are properly extended. This is accomplished through the locking washer and the bushing that carries the jaws. Because the backside of the bushing is cut at an angle, the spring force causes the locking washer to tilt, which causes the washer to lock. In doing so, it prevents any backward movement of the bushing, which means the jaws cannot expand. If this washer is straightened and held perpendicular to the shaft, then the spring can be compressed and the bushing slid backwards to allow the jaws to expand. Straightening the washer is accomplished through a sleeve that mounts between the click-clack housing and the click-clack fitting installed in the door. We will show this installation by hand without the click-clack housing for clarity. As the center shaft travels into the aircraft receptacle, the jaws are locked because the washer is still tilted. As the click-clack nears the end of its travel, the washer contacts the sleeve. As travel continues, the washer is straightened and the jaws are unlocked. By this amount of travel, however, we know that the jaws must be fully inside the fuselage receptacle, and it is safe to allow their expansion. As the extension continues, the ramp on the center shaft pushes the jaws outward, which is the click-clack's expansion process. The jaws of the click-clack are now fully expanded and seated inside the receptacle, which now transmits loads through the door and makes it a part of the aircraft structure. For the click-clack to be able to carry its full design load, the center shaft must be extended the required amount. This is because it is the shaft that supports the jaws in carrying these loads. As shown in this simple drawing, the ramp portion of the shaft does not provide support for the jaws and could allow the jaws to bend under load conditions. With the shaft properly extended, the jaws are totally supported by the shaft to prevent bending. Two bayonets, located near the bottom of the cargo door, are also installed. These are designed to help align the door with the fuselage as necessary, so that the click-clacks can be easily engaged. The mechanism that operates these bayonets has been designed to push them into the door opening prior to the engagement of the click-clacks. Two handles, one inside and one outside, operate the latching system. Each of these handles is connected to a common shaft that rotates a bell crank attached to the shaft. Push-pull rods transmit this motion outward to additional bell cranks. Each of these bell cranks is attached to an additional set of push-pull rods that are connected to the click-clacks and bayonets. All of these mechanisms are designed to move to an over-center position when the door handle has reached the fully closed position. This makes the door locking non-reversible without rotating the handle. An additional tube and spring assembly, connected directly to the handle, are used to stop the handle itself from moving without intentional external force being applied.
Probably no subject is as hotly debated in Merlin and Metro maintenance as is click-clack lubrication. Everyone seems to have an opinion, each person convinced that his idea is the best. Over the years, the factory has approved many different materials, techniques, and intervals. The real bottom line is this: if you're a new operator, follow the factory's recommendation. If you're an experienced operator that has found a system of click-clack preventative maintenance that is producing good results, stay with it. Probably the #1 golden rule of aircraft maintenance is, don't try and fix what ain't broke. Now let's return for the conclusion of our program.
The handle bell crank also contacts the door seal inflation valve. This valve will open to allow 18 psi air from the de-ice pressure regulator to be routed to the door seal. When the door seal inflates, it will seal the door against a loss of pressurization. The geometry of the bell crank that actuates the valve has been designed so that when closing the door seal valve will not be actuated until the latching mechanism is near fully engaged. When the handle is moved to the open position, the geometry is such that the door seal valve will be actuated closed, which removes pressure from the seal and also dumps any trap pressure prior to the retraction of the latching mechanism. This is so that latching or unlatching of the door is always accomplished with the door seal deflated. If the seal were not deflated prior to closing the door is not likely to be closed, as the seal will prevent the door from fully going into the opening. Worse yet, trying to force the door closed could damage the seal, as the inflated seal is larger than the gap between the door and the door opening. The door opening in the fuselage contains the fittings to receive the click-clacks and bayonets. A warning system to inform the pilot of the door status, either fully closed or unsafe. An attaching point for the door hinge, and attaching points for the door opening snubbers. The fittings, or receptacles, installed in the door opening are cast assemblies that mount securely into the aircraft structure. Each receptacle contains an eccentric bushing that may be rotated to adjust the alignment of the click-clack and receptacle. These bushings are available with different amounts of eccentricity for use in correcting alignment problems. A locking plate is used to prevent future rotation of the bushing after it has been properly positioned. This plate is secured through the receptacle faceplate screws. The fittings that receive the aligning bayonets are in a fixed position and do not incorporate eccentric bushings. The door hinge plays an important part in door operation. It carries part of the load imposed on the door in flight and supports the door in the open position. Additionally, since the hinge is a fixed point, it, along with the aligning bayonets, are the critical factors involved in aligning the door into position. In short, if the aligning bayonets engage properly, but the hinge is warped, cracked, or worn to the point where it is not maintaining its rigidity as a fixed point, then the door will be extremely difficult to fully close and lock. Assisting in lifting the door and holding it open are two gas spring assemblies. These are sealed units with no maintenance requirement other than remove and replace. A warning system is installed to inform the pilot of the status of the cargo door latching system. Indications to the pilot consist of a red cargo door warning light installed in the annunciator panel and a cargo door warning test light and circuit installed in the co-pilot's forward side panel area. A dual-function micro switch is installed within each receptacle assembly. The switch plunger will be actuated when there is full engagement of the click-clack. These 8 micro switches are wired in series and are connected via a relay to a red cargo door warning light installed in the annunciator panel. There is also a switch installed next to the cargo door handle mechanism that will be actuated when the door handle is in the fully closed position. Since these 9 switches are wired in series, all must be fully made by each one's respective click-clack and the door handle fully closed before the annunciator light and red test light will extinguish. Any single unmade switch, whether click-clack or door handle, will cause the red lights to illuminate. The position of the click-clacks can also be visually inspected through clear plastic inspection windows in the door. Red markings on the click-clacks are used as indicators to determine its position relative to the amount of engagement in the receptacle. For simplicity, only 2 of the 8 click-clack switches are shown in this drawing. The cargo door test circuit consists of a test switch, cargo door warning relay, red door open lights in the annunciator panel and the co-pilot's switch panel, a green cargo door switch test light installed in the co-pilot's side console, and the switches installed in the cargo door itself. The test switch serves a dual purpose. In this position, it tests the cargo door switches and associated wiring with the door open. If any of these switches were to jam in the closed position, it would compromise the integrity of the warning system. When the test switch is moved to the test position, it checks to see that there is a path through each of the click-clack switches and the switch on the door handle. This path will provide a ground to illuminate the green light on the co-pilot's switch panel. In this other position, it checks out the bulb and ground circuit. When the door is closed, the series path formed by all of the now closed click-clack switches and the door handle switch will provide a path to energize the cargo door warning relay. When this relay is energized, it breaks the path to ground for the cargo door warning lights installed in the annunciator panel and the co-pilot side console. Both will extinguish. These same 9 switches, 8 activated by the click-clacks and 1 by the cargo door handle, are also used as part of the cargo door test circuit. This circuit is used to test the continuity of the cargo door warning system and is a convenient place to begin troubleshooting activities.
Well, that covers the cargo door system. With proper maintenance and operation, the cargo door system will cause minimum problems. Until our next program, good flying and good maintenance.